Okay, yeah. So on Monday, I taught you about my two cents about what quantum graphs are, and today it's even less money maybe. So just 1 cent about what we can say about the correspondence between quantum graphs and quantum channels in the setting I taught you on Monday. So let me start with correspondence from graph to channel. Oh, sorry, quantum channels to quantum graphs. So that's the like easy direction in a way. So if you have matrix algebras, you want to model quantum channels by maybe trace preserving completely positive maps, and the well-known correspondence is by taking transpose. You can also model them by unital completely positive maps, UCP maps. And for finite dimensional C-star algebras or multi-matrix algebras, it's better to work with this second picture, UCP maps, and maybe think about what you can really say about like densities and states afterwards. So let's say we have a map of finite dimensional C-star algebras that are unital completely positive, UCP map. I don't know. Maybe I should try to put it. And morally speaking, this gives you something like pullback map of observables under the channel. So you want to think of actually channel represented channel from a system represented by the B to another system represented by C, but phi is like pullback map. Anyhow, formally we look at UCP maps. Then once you have a unital completely positive map like this, you can construct a kind of tensor product with that takes into account of this phi. Call it, I mean, this is just ad hoc notation just for today. What's that? It's the quotient of C tensor B. So the moral is we want to have something like Hilbert space where C and B act in commuting way, but not really fix a scalar inner product. You take the usual tensor product, but then introduce a B-valued inner product. Defined like this. So this way, I mean, the right-hand side is in B on the node, and it satisfies the positive semi-definiteness. So if you have like some of such simple two tensors. Sorry? Oh, sorry, pi. Yeah, thank you. Oh yeah, theta equals pi everywhere. So I wanted to. Sorry, I changed my notation somewhere, and sorry about confusion. So, so this is a very defined B-valued inner product, and well, so it looks a bit complicated, but what's good? I mean, first of all, so there's a commuting action of C and B on this space coming from the sort of natural one on this tensor product. So the one point is CB bimodal structure. Okay, C acts from left and B acts from right. Just by this. But also, there's a nice map that models Stein spring dilation from B into this X. It's so the most obvious map when you have input in capital B. You just take tensor product with the unit in C and get this. And what is good is the phi being unital completely positive guarantees that this is isometry of B-valued inner product spaces. I mean, so this one also becomes a B-valued inner product by something like B1 star B2 being the inner product of B1 B2. And like I said, let's name this V phi. And so this is really a variation of Stein spring dilation for UCP maps. Sorry. So I meant I used this to emphasize that it's a map of B right B modules. Yeah, sorry. So again, it's a bit confusing. Maybe I should put C. But important thing is this is just a map of right B modules. Anyhow, so that's good enough. And so the first thing is so if you look at the left action of C on X sandwiched by B, so B star phi lambda C phi. Overall, this is a linear map acting on B, and it's just left multiplication by phi B. Phi C. And also, like I said, B is actually a map of B modules, right B modules. So it intertwines this row B and right multiplication. This is just spelling out what I said there. Row B. So V phi composed with right multiplication.
Wait, understand. So BB, when you write BB, you mean that as a module with respect to phi. What is the scalar product of BB?
Phi, right? So this one doesn't have to do with phi. I mean, it's just the
usual one?
B1, B2 is B1 star B2. Well, because phi is UCP map, unital map. So that's but good to sort out the conventions and why we want to work with UCP maps instead of general completely positive maps. So otherwise, we wouldn't get the isometry. So this is really the sort of spelling out what you expect from Stein spring dilation in a bit more sort of invariant form. Okay, right, and so we have this Stein spring dilation, and then we can define a contant graph on B that represents something like the confusability graph of the corresponding channel. So say S phi, what's that? So this is sorry, maybe I should be a bit precise. Yeah, yeah, I guess psi is here a state, trace shell positive functional, and so that I don't have to worry too much about the relation with the modular operator. Yeah, so this way I get a space of linear maps acting on B. Okay, V phi starts from B, ends up in X, and lambda C prime. So this is the commutant of C acting on X. Okay, and then V phi star brings it back to B. So yeah, here again, yeah, maybe this is a bit like overloading the notation. So it's just a set of linear maps. Yes, so what I mean here is the commutant of lambda C embedded maybe as a subset of linear map acting on X. Yeah.
Do I need to worry about jointable?
No, I mean, so, well, the action is adjointable. So you do end up in the adjointable subspace, but here I really need to take the commutant inside the linear transforms anyways, so not just as.
Yeah, so you don't care about bilinearity, for example?
Well, so the, yeah, I mean, I really want to take the, so, I don't want to stick to B modules, B module homomorphisms. So for example, what I get is actually by the second observation. So if I look at the like so pre-composition with white multiplication by B, then I can absorb that inside V phi, right? So, so actually I have this important property. Maybe I should. Yeah.
So the thing you've written down gives me transformations of B.
Yeah, yeah.
And then I confuse that with L2B.
Yeah, yeah, sorry. So maybe this is, again, I should just write Lx, yeah. Sorry, Lb, because here, I mean, yeah, yeah. So the only claim I want to make is I get a subspace of these linear maps acting on B, and then once you fix positive functional, I get the operator system on L2B. And if that functional is a trace, then this is really a contact graph in the sense I said. Space for positive functional. Of course, I mean, then you want to like understand how psi, choice of psi gives you scalar inner product on x and b, but once you have b valued inner product and positive functional on b, you can get the scalar product also. So that part is in a way it's always doable, but if you want something like if you want some invariant way to define things, maybe better to do that early.
Yeah, this is an operator system.
Well, because again, so by the if you define scalar valued inner product on x by psi, then the C representation of C is by unitary representation, star representation. So this gives me subalgebra, and this is also subalgebra, which is the operator system. Okay, so that's a easy implication, and maybe let me spend like very quick 15 minutes to say what we can get out of this graph about the channel. And so there are several important invariants about the channel we can draw from this graph. But so I think the earliest one historically, and one of the most important one, is the idea of independence number and zero error capacity for the channel.
Yeah. One question. So how is it related to the operator system that Sam was defining?
Yes, so it's exactly same. Yeah. So again, so this can be a bit confusing, but if you start with if the B is a matrix algebra, and then so up to amplification, it's the its usual definition sum J. Why? Because in the end we are working with this, and that has Stein-Spring dilation. It's I mean isometry in that Stein-Spring dilation, the adjoint, and this one. And for example, if for the moment you can maybe take my word, and I will try to give you a way to see why this reduces to the classical definition later. But yeah, so this really reduces to the classical definition.
Conjugation B phi relate in any way to the complementary channel, what they say?
No, I mean, so this is really just the having to take ki star kj, and so the ki star comes from v phi star, and the way you can pick up different indexes I and j have to do with taking commutant in some representation, but
have your ancillary space in the file strength. Yes, exactly. So
oh, maybe, yeah, then.
Looks like the complementary system.
Yes, yeah. So maybe, so in that way, yeah, sorry. So I think I mixed up what you wanted to, yeah. So the more like the middle commutant has to do with that, yeah. Yeah.
So if there wasn't this inner product that's sort of connecting what's happening in B and C, then what you've defined here would kind of just say, take everything in B, put it inside the tensor product, but everything's going to commute with left multiplication by C. So you're not doing anything. And then
E-
somehow the
well,
product is
yeah.
going to give you that this becomes a more interesting, like, is that?
Well, yeah, although, I mean, so the B phi starts with, start from just B, right? So there's no obvious action of C. So, yeah, so it's a bit difficult to like really put something like commutation with C in the end, I think.
You've done a quotient when you define this.
Yeah, so the X does have action of C, so that's fine. But, you know, B phi starts from B. And so this one doesn't have obvious action of C. I mean, it only receives completely positive map from C. But this is not the algebra homomorphism. So yeah, so there's no obvious action. And in a way, X is the approximation of that. I mean, X does have action of C. So you sort of blow up B into something like direct sum of B that does have action of C. And then B phi just cuts down that blow up into original copy of B. Maybe this is one way to think about that. Yeah. So overall, I mean, it's only, so it does belong to the, yeah, I'm afraid somehow the way this works, like it's not quite module homomorphism in the end, but yeah, somehow it works exactly in the way we want. Right, and so let me explain quickly about the independence number. Although here, I'm afraid I cannot really like prove things in any way, so just motivating things. So if you had the classical channel, so that's just there's input set, output set, and the classical channel is formally modeled by something like collection of independent random variables on the output set labeled by the input set. And then you get the confusability graph saying that the you connect two inputs if the corresponding random variables can take same value. So and yeah, and then so we want to see when we can send like distinguishable information by this kind of noisy channel. Then so there is a number called independence number for that you can define purely in terms of the graph gamma f. This is just the maximal size of empty subgraph in the graph gamma. So say maybe, by the way, I am formally defining, so there are loops at each vertex. So no edges between distinct vertices, of course. And so if you have such subset A, then if you take inputs from this subset A, so they don't get confused under F, right? So, and alpha gamma F, so this is really just the maximum number of different inputs that you can send to F without error. Okay, and right, so the corresponding idea for the content graphs is already sort of worked out by original papers by Durand, I think. And so if you have a content graph to be visualized on matrix algebra, then you can define something like this using state vectors and orthogonality with the operator space S. You want to define starting from here. I am cheating a bit. I mean, so my convention was to define content graph as operator system inside B of your algebra that by modules for the right action. But you can always cut down that to some corners, and then for matrices, you can just talk about usual operator systems without bimodule property. All right, and then from this, we define alpha S to be just the max of defined choice of vertices, so to say, but you choose state vectors. So say 1, 2, 3. And so that kind of having no edges correspond to the rank 1 operator that you get by take inner product with one of psi i's and then output another psi j should be orthogonal to S. So S. Course, with defined choice of indexes. So this means defined input states can be still distinguished after applying the quantum channel. Yes, so that follows from identity being in S. So if this is orthogonal to identity, that means so they are orthogonal. Yeah, but still, yeah, of course, good to note. Yeah. IDE. Yeah, and so again, I mean, so this has obvious interpretation that so this is the maximum number of defined inputs that you can send to quantum channel N. and that's sort of transpose of the phi, and without losing orthogonality. Okay, right. And then, so there's a interesting thing called super additivity or maybe super activation for the channel. Is that you can have in a way graph that is too big. That means the k alpha s is as small as possible. So you cannot really like have orthogonal rank 1 maps in the complement. So then sort of content graphs being big means the independence number being very small. And but if you take the tensor product, that can be bigger than 1. So this is the super additivity of this independence number. And it means if you take 2 noisy quantum channels and send information by these noisy channels, the overall sort of composite can have like some zero error communication. Anyhow, so this is something you can concretely construct on the 4x4 matrices. Right, but of course, classically this is impossible, right? So this condition for graph gamma means gamma is a complete graph, and if you have a complete graph, and this corresponds to the graph product, that's again complete graph. So you cannot have this for classical graphs. Again, so up to the convention that you can normalize graphs to have loops around vertices or not. So that's a matter of convention. And up to that, alpha gamma being 1 is the same thing as being complete graph. So, okay, and ideally, we want to find something like this for general UCP maps between non-commutative C-star algebras. And well, you can, so that's the message. But in the end, you just do bookkeeping starting from Duan's example or other examples built on matrix algebras and carefully check that you can work with these finite dimensional C-star algebras you realize inside matrices. Anyhow, let me explain how to at least make sense of this independence number for general finite quantum spaces instead of just matrices. And then let's be happy with that. So we see that there is a connection between these complete graphs and independence number. And actually, we can phrase this kind of correspondence using graph homomorphism. But of course, to be precise, it's not the graph homomorphism of the complete graph into gamma, because if you stare at this, it doesn't quite work like A supports a copy of complete graph. It's the complement of gamma supports the complete graph on A. So let's say we have a contant graph, G, modeled on finite dimensional algebra, positive functional, and adjacency matrix. Then we can make sense of the complement graph by basically taking the difference of A with the matrix of 1, 1, 1s, or adjacency matrix for the complete graph. And then it's given by A, say, bar, that's eta, bar, A. So what was eta? Eta was the embedding of scalar into B. Eta star, it's just applying psi functional. And so this is actually an adjacency matrix of some contant graph on B, the empty graph, the complete graph. And then we just take the difference of this adjacency matrix of complete graph with A. And you can check that it satisfies the consistency condition for the adjacency matrix. And the last part, adding identity, it's just a matter of normalization. So either to put 1, 1, 1s on the diagonal or not, that you can always adjust. Okay, so that's a complement graph of G. And then we can look at the graph homomorphism problem from the complete graph into this complement. Of G. Oh shit, let's say N. So here there's a bit of choice. Like in some talk, it can be, local scheme or quantum scheme or blah. And well, so it's concretely given by theta homomorphism from B into Cn tensor some C star algebra C, right? And so this T specifies what kind of C star algebra you want to have here, either commutative or finite dimensional or just any C star algebra. And then, so that theta should intertwine Mn into S up to this C. So this is what we expect. So we see that the you want to squeeze in matrix algebra into the operator system. So that's the game to solve, right? And you can use this sort of ancillary system C. And well, for classical model, if you so sorry, how do I say? So if biggest such n was 1, so that means S is too big. Original graph is too big, so that the complement graph is too small, just empty graph. And but then maybe so if the complement has some size, you can start to squeeze it in. So that's the idea. And yeah, and then for non-commutative algebras, we can actually start to have something like funky feature, like even if the original graph has 1 for the maximal n, the tensor product can have bigger n. I mean, because of the way tensor product operator system work for matrices. Okay. Anyhow, so I guess I'd better try to wrap up. And let me explain the inverse problem for the first topic I explained. So at first, I explained how to get quantum graphs out of quantum channels. And then, well, there's inverse problem to get quantum channels out of quantum graphs. And the thing is, this is one way or another easy to understand because it's really a concrete problem about operator systems. And then if you want to say something about UCP maps, starting from quantum graph, where you can solve this problem, maybe you want to recover or you want to find some quantum channel with the expected super activation property. Okay, so and again, the inverse problem was actually stated by the original paper by Duan, where he, I guess, did all these super activation for channels. It's very classical topic in this business for Duan, by Duan. And also, so I think essentially by these people, Tibit, Chen, and Harrow, I think. It's a very nice name to do quantum information. Yeah. So they found that the starting from quantum graph on matrix algebra, you can become a channel that gives the original quantum graph. Of course, there's no uniqueness about such quantum channel. So yeah, also, sorry, so I think I attributed super activity to Duan, but so these people also did that. Sorry, so I should have mentioned that. So B equals MD, say, and operator system S inside, one can find a UCP map from another C-star algebra to B that gives S as the confusability graph. Right. I mean, so they placed it in the advantage of dual trace preserving completely positive map, but of course, we can go back and forth. And let me briefly review what they did. I mean, how they constructed C and phi. You want to start from choice of P or VM inside S. By right. I mean, usually people take it as a basis. That's of course doable, but you don't really need that basis property. Important thing is you have sequence of positive elements that add up to 1. And yeah, then yes, sorry, yeah, of course, spanning property, yeah, sorry, thank you, span S, yeah, otherwise, of course, it's, you don't get anything. Okay, and then write xi equals ai star ai. I mean, if you want, just take the square root of xi, but any solution works. And C is going to be MD direct product M times. I mean, if you don't like this, you can embed this into MND. So that's what they did, I think, if you want to stick to matrix algebra. And right, then what I want to do, I mean, I need to give you a unital complete positive map from this C to B, MD. And so sequence of D by D matrices. Okay, and that's the input to phi, and you do this. And then it's a UCP map by POVM assumption. And right, my claim is this really gives S. And again, well, so I guess I have to cheat a bit, but not too much. So if you look at the representation of T on n-dimensional Hilbert space by this embedding, what's the commutant? You have something like block diagonal matrices, n by n block matrix. I mean, block diagonal matrices, and the commutant is just the again block diagonal, but having scalar in each block component. Okay, maybe I can get this. So if you want to compute the B phi, what would be this? Again, with slight cheating. What's the cheating? So the V phi, I can model that by applying the AIs to input, one input, V phi. Yeah, maybe X is just the AI X. Okay, and then I'm going to act by the lambda C prime, that's the diagonal matrix, and oh sorry, so I promised to give you the form. So lambda C is something like block diagonal matrix. This form. Then if you take the commutant of such block diagonal matrix, that's the scalars on each block factor. And then after taking product with lambda C prime, I can pick up like arbitrary linear combination of AIX, and then again taking product with the yi afterwards. Sorry, what am I saying? So that's just taking arbitrary product of linear combination of AI, and then V5 star, of course, that's the taking product by adjoint of AI, and V5 which is just the something like AI star AI, and so X is an input vector, and then you end up getting span of AI star AIs that are Xi's that span operator system S. So for any input vector, I get this kind of computation. And so that's how you see that the, so we get that equality. Okay, and so maybe we can see what happens if we instead just have matrix algebra here. No, sorry, what am I saying? So instead, if we have if the commutant is not just block diagonals, but if the commutant just copy of n by n matrices, so putting scalar on any block component, not just on the diagonal, then you can mix AI star and AJ. So this is how you get usual contour graph, starting from class operator. Yeah, sorry, maybe this is a bit confusing. But so this way you can recover S out of this string. And then, so how do we generalize this to finite dimensional system algebra in general, beyond matrix algebras? So that's my last 5 minutes, I guess.
Can you say what the
Sorry?
Can you say what the bimodule is?
Well, I mean, so in this case, just a moment. I'm afraid, I mean, other than like the definition I said, it's not super obvious, I think. I mean, you start from C, which is just that, and then, yeah, so I think it's going to be, morally speaking, it's going to be something like YI, AI, ZI, and you work with this kind of composition where YI, ZI are in MD, and then treat these n tuples, such n tuples. So you can have some kind of terms passing through AI when you have, for example, when you obvious thing is you can take scalar multiplication yi or zi, and so do the obvious identification. But if you put something like t here that commutes with AI, then you can pass through that to zi side. I mean, so really work with this composition. So I think that's what it is. Okay, and right. So the proposition, the final remark is we can find such phi and c for a general B without assuming that you have a matrix algebra as the target. Okay, and so how do we find that? I mean, in a way, it's a bit cheating, or maybe just building up on this Duan's construction and making sure that you land in B instead of some bigger matrix algebra. And so one thing you can always do is treat S as a contant graph on this bigger algebra, not just B. And then do Duan's construction and find some UCP map from this direct sum of matrix algebras. But then you end up in this bigger algebra, not in B. So we just want to make sure that there's a way to modify that and land in B instead. Or take. So to make it precise or concrete, let's take a finite subgroup in the unitary group of the commutant. So commutant is just the white multiplication operator. So I am saying take a finite subgroup in the unitary group of B. And big enough so that they linearly span, the elements linearly span B, or maybe B prime. Then you can just do this averaging on pi by G. So this works. I mean, so if you define phi hat on n tuple of matrices, to be precise, I guess C is just to B or to B times, and n is a choice of P of M spanning S as before. N is the number of terms in the P of M as above, and just do this. So you see that it's just a composite of original construction by Duan and averaging by G. And so this makes the wizard commute with any element in G, but by this linear spanning, it's going to commute with any element in B prime. That means you are in B. So this is in B. Okay. And
averaging over G, does that give you a conditional expectation?
Yes, yes, a very good point. So actually, so every time you have a conditional expectation from B of H to B, you can just do this. So I just wanted to make it a bit concrete. So in Weaver's formulation, I mean, if you don't have just finite dimensional system algebras, but like general polynomial algebra, then that's the way to go. So yeah, I guess hopefully with Matthew, I try to like write a quick paper around this, and hopefully add something a bit more if we manage to. But so this is the like, work in preparation. So in the infinite dimensional case, so this having conditional expectation, that's a non-trivial extra assumption. But for finite dimensional case, I mean, there's always a way to concrete like that. And yeah, so you have something like Duan's construction for possibly infinite dimensional case, ending up in B of H, and then compose that with E, and you get the UCP map into your target algebra. And of course, you still need to work out this V phi lambda C prime V phi to check that you have the quantum graph. I mean, you started with, but that's really something one can work out. And right, and finally, yeah, well, maybe I'd better stop. So, yeah. Well, not quite. I mean, so the only thing I am saying is the way the way you construct. Oh yes, good point. Maybe actually no. Yeah. Yes. Yeah. So this direction, I guess we don't have to trace condition. Yeah. So you do start from S. That's really in B of L to B. Yeah. Okay. And so this construction works. Yeah, I mean, so the other direction, if you start from channel, then you do have to assume that it's trace. Otherwise, there's no hope to get consistency with modular operator in general. So yeah, let me just say it in words, but then so you can just compose this construction with what happens for matrices and get super activation type result for the corresponding channels. But I mean, so that's again, you need to compute. Like you don't lose this independence number by composing inclusion, composing what you have for matrices and inclusion of your finite dimensional system into matrices. So there's another bookkeeping to do. But if I'm not mistaken, so that should be also okay. Yeah, thank you.
Any questions?
Really stupid question. Why is it called super?
This one, I mean, from what I understand, so you have something like, so this zero error communication from a composite of noisy channel. And so it's, so I think the terminology is from older paper by Shaw and his collaborators, I think. And, but maybe you know better.
Cannot transmit any information with zero error. Right? And if you apply twice for parallel, all of a sudden it activates itself.
So activating just means like getting zero error communication, I guess.
Acting as a catalyst on its own.
I have another potentially dumb question. I'm not saying yours is dumb. But the super parts that anything to do with, because like I know like in QI they love talking about super operators or super maps, right?
This is more like super additivity. So
I think super is because I mean, so there is the original result for the first observation I did was you have two channels with zero error capacity, zero. You can when you tensor them, you get something larger than zero, but they were different in the beginning. And then super is when you have the same channel, P tensor to P.
But Duan also has different channels.
well, so he can start from different channels and just combine them to have the same channel, I think.
If you just increase capacity by taking standard product, it's like activation.
Oh,
You make it from zero.
Yeah, so it's more about this super additivity, so having strict inequality.
Okay, so it's not the same use of the prefix, or rather, it's just coincidental.
Yeah.
So are there any bounds of how far you can go from zero?
There are works on that.
Right.
not everything, no. You can take, for instance, all those capacities that you can take in terms of product, maybe divided by something reasonable, I don't remember. And question whether, suppose such a limit from the beginning was 0. And if you take two such channels, whether the product has some such not 0. Actually, in some works, this is called zero error capacity. And what Makoto was talking about, one shot 0.
Yeah.
And what general zero error is less known, but also there is no.
I wonder if there is some monotonicity of these independence numbers or quantum independence numbers.
Yeah. So there are the obvious ones. I mean, like if you compose, then there's a obvious decrease because of operational interpretation. But yeah. But other than like super obvious ones, like so these things you can say in plain words, I don't quite know.
If you take not complete graph, but quantum.
That's also a good question, I think, that I don't have any example. I mean, of course, then like what you mean by the, yeah, let me be, yeah, of course, I mean, so the quantum homomorphism problem makes sense perfectly, yes. But then you end up having not just like numbers for the size of complete graphs, but like all these continuum. I mean, so B and psi, and maybe you stick to something like delta forms. But still, yeah, I don't have any intuition, to be honest. But yes, I guess one can have something like super activation for that also. I mean, super additivity of independence numbers. Yeah, okay.